Derivatives play an important role in optimization. So in this video, I would like to review some of the basic definitions that will be useful for our purposes in the context of optimization. We first defined the concept of directional derivative. Well, the idea can be seen as the following. Let's consider a point x, which belongs to Rn, and let's take a direction starting from x. Well, this direction is characterized by a vector d, which is also in Rn. And what we would like to do is to understand the behavior of the function f starting from x in the direction d. To do so, we do a step of length alpha in the direction d. We obtain a new point, which is x plus alpha d, and then we measure the value of the function at that new point. So the idea now of the derivative is to compare the value of the function of the new point with the value of the function at x. So this is the numerator of this expression here. This is the value of the function of the new point after having followed the direction d with a step alpha, and the value of the function at x. And we normalize it by the step length, by alpha. The directional derivative is this quantity when alpha goes to 0 and staying positive. If the limit exists, it's called the directional derivatives. And we will use this notation here that I will describe later on. So this is the notation of the directional derivative that is well defined if this limit exists for a direction d. If the limit exists for any d in Rn, then we will say that the function is differentiable at x. And actually, in our context, we will assume that all the functions that we are dealing with, not only the functions that are used for objective functions, but also the functions that are used to define the constraints, we will assume that they are differentiable. Now, if we look at specific directions, in particular the axis of coordinates, we can calculate also the directional derivative along these axes. In this case, the directional derivative will be called the partial derivative. So in this notation, EI is a vector of all zeros except one at the ith position. So this is an axis of coordinate. The directional derivative along the axis of coordinate is called a partial derivative. And if you put all the partial derivatives together, so if you take the partial derivative with respect to the first variable, then with the second variable, all the way to the nth variable, you obtain a vector of Rn, which is called the gradient. And the notation of the gradient is nabla f of x. And actually the notation that we used before, which was nabla f of x transpose d for the directional derivative, well, this notation is actually an inner product, because if nabla of f of x is this column vector, which is the gradient, when it's transposed, it becomes a row vector, multiplied, so this would be nabla f of x, multiplied by the vector d. So what we obtain is a real number, which is actually the inner product between the vector gradient and the vector d. This is the directional derivative that we have seen in the previous slides. This will give us a very important information about the function. Indeed, if a derivative is positive, it means that the function is increasing along d. And if the directional derivative is negative, it means that the function is decreasing along d. So we characterize this by identifying a descent direction. So a descent direction is defined as a direction such that the directional derivative is negative. It means that if you follow the direction d starting from x, well, the function will decrease, at least a little bit. Now, the concept of derivatives can be generalized for a set of several functions. So now if we have the function f which maps Rn into Rm, so it means that instead of producing one value as we have in the general objective function, the function f generates m values. And if it is continuous, everything that we discussed before is still valid. So the gradient now becomes the gradient matrix. So for each of the m values that the function generates, we can calculate the corresponding gradient. And each of these gradients becomes the column of this gradient matrix. The gradient matrix is defined as a matrix that has n rows, where n is the number of variables, and m columns, where m is the number of values of the function, and the element ij is the partial derivative of the function number j with respect to the variable number I. In algorithm, it's sometimes common to use the transpose of this matrix, which is called the Jacobian. It means that the gradient of the various functions are organized by row instead of by columns. The derivatives will be used in this course both to analyze the problem itself and to define the algorithms. And from now on, we will assume that all the functions involved in our analysis are differentiable.